Hey, welcome back to Calculus. In this first of two lectures on section 6.3, we're going to look at an alternative method for computing the volume of a solid of revolution, and that method is called the method of cylindrical shells. All right, so in this lecture, I want to derive a formula for it, try to motivate why we need it, but I want to derive a formula for computing volumes by cylindrical shells. So it comes in handy when our previous method of disks and washers will let us down. And then I want to do just a couple of examples showing how to compute with this new shell formula, revolving things about the y-axis. Okay, in the second part, we'll turn our attention towards other axes, but in this lecture, we're going to stick to just the y-axis. So let's motivate the method with an example that won't work very well if we were using disks or washers. All right, so I'm going to take this cubic polynomial, f of x is 2x squared minus x cubed, and look at a plot of it over the interval from 0 to 2, and the region that's bounded by the cubic polynomial on the x-axis. All right, so it's shown in blue there. You can see that I've labeled the polynomial with the equation y equals 2x minus x cubed there. And I want to revolve this thing around the y-axis. Okay, so why do we need a new method? Well, remember that when you're using disks or the washer method, that your region, your local estimate, your segment, or in this case, the author's drawn it like a thickened interval. It's got some thickness. So this segment right here, it has to be perpendicular to the axis of rotation. Okay, well, that means we're going to need to take this equation and solve it for x in terms of y, because that's how we're going to find our so-called outer and inner radii. Yeah, to use the washer method, we have to subtract the outer radius squared minus the inner radius squared, and those outer and inner radii are going to depend on y, so we'd have to solve this equation for x, okay, because we need y to tell us what x is. But how are we going to do that? It's a cubic equation. It's not impossible to solve cubic equations, but you can kind of see that it's going to be a little tricky because somehow for this given y value, there should be two solutions, x equals this, x equals that. So maybe we'll have to take a cube root somewhere. I don't know. Algebraically, it seems difficult. So we're kind of stuck trying to use the washer method, and that's kind of the way I'm trying to motivate this. Whoops, I didn't mean to do that. I'm trying to motivate this idea that we need some other method. This segment being perpendicular to the y-axis is kind of ruining it. All right, so what we kind of need to think about is, well, since things are defined in terms of x, wouldn't it be nice if we could take a segment that was parallel to the y-axis? So I'm just going to draw it in here in my usual segment color green. If you want me to thicken it like the author is, you could think of it as a rectangle if you want. So you're thinking about this thing. Okay, that thing depends on x, not y, so that's kind of nice because we have our function given in terms of x and not y. But now we have to wonder, well, what kind of shape does this green rectangle form? What kind of solid region does it form when we revolve it around the y-axis? Yeah, that's kind of my crude picture of it there, but you got to kind of visualize in your mind's eye. Maybe stop the video and think about it for a second. Like what kind of solid region is this rectangle going to sweep out? It's not going to be a disk because we're not revolving it around the x-axis, but rather around the y-axis. So if you thought about it for a second, I think you'll agree that it's going to sweep out this thing that we call a cylindrical shell. All right, so if I kind of tried to show you using the same color, that rectangle in the previous picture, I'm sort of visualizing it like it's right here in this picture. Yeah, and then the y-axis in this picture would have been the line running straight down through the middle of this thing all dotted, so it's like behind it. Right, so when that green rectangle revolves around that y-axis, it sweeps out this cylindrical shell. So that's what I mean by a cylindrical shell. So it's sort of the region in between two cylinders that are same center, two concentric cylinders. And how do we find the volume of such a thing? Well, I don't need the exact formula for it because we're going to let the thickness of these cylindrical shells kind of go to 0 when we take limits of our Riemann sums. So this cylindrical shell, you can see in the picture, it has two radii. It's got kind of an inner radius R1, the authors labeled it, and a slightly bigger one, R2. Let's just choose R to be sort of their average. All right, so that's the R I'm using in this picture. And if you imagined kind of slicing this shell, take a knife and cut it right down through my green rectangle, top to bottom, and then kind of imagine it's made out of clay or dough or something that you could just sort of unroll it. Yeah, so unroll this shell. Oops, can't spell unroll. Unroll the shell into this slab over here. Yeah. And what are the dimensions of the slab? Well, the slab has a thickness. That's the thickness of our shell. That's this delta R, the author is denoting it. The shell had a height, h. That's exactly the same as the height of our slab, yeah, when you unroll this thing. And then what about this? This is the trickiest dimension. How long is our slab? Well, the length of the slab would come from the circumference of this circle. And we were using an approximation that the circle has radius r. Well, the circumference of a circle of radius r is 2 pi r. So when you unroll that thing, that's how long this thing would be, approximately, using the average of r1 and r2. So the volume of that thing is approximately 2 pi r times h times r. All right. So let's go back to our coordinate system. How do we write down this thing in terms of our x? How do we make our local estimate? So I'm going back to sort of a generic picture, okay? So I've got not that same function that was drawn above, but just some function, y equals f of x. It's bounding some region between two x values a and b, the usual setup. And I've kind of drawn in here, well, a green rectangle. You can see it. So I'm imagining this thing rotating around the y-axis, forming this cylindrical shell. So I drew it over there. The thickness of the pen in this picture on the right is supposed to be the thickness of my shell, delta x in my notation. So if we unrolled this shell into this slab, I tried to draw the slab nicely. Once again, we have to just think about its dimensions. Well, it's delta x thick. What's the height of this shell? Well, the height of the shell depends on x, yeah? The height of the shell is the y-coordinate right there. That y-coordinate depends on x. It's f of x. So the height of this shell is going to be f of x. In the picture, it looks like they're going to get sort of shorter as x gets bigger. But whatever it is, it's f of x. And then what about the circumference? Well, the radius of this shell, the distance to the axis, is x. So the circumference of this thing, it's going to roll around a circle of radius x. A circle of radius x has circumference 2 pi x. So the local estimate for our piece of volume here is 2 pi x. That's the length. 2 pi times the distance to the axis of rotation. F of x, that's our height. Delta x, that's our thickness, okay? Length times height times thickness is volume. So that's a local estimate for our volume. If we slice this thing up into many such rectangles, there's a nice picture I took from the book. We can look at it. Here the author's slicing that region into 1, 2, 3, 4 rectangles in the picture on the left. Each one of those rectangles swings out a cylindrical shell, and those cylindrical shells fit together to give an approximation for our volume. So notice it's kind of a different way than discs and washers, where we were slicing it up into a bunch of slices. This is like slicing it up into a bunch of things that fit inside of each other. But at the end of the day, it still decomposes the volume, right? The sum of these 4 cylindrical shell volumes should be pretty close to the volume that we're seeking. So I'm writing it down here, trying to use this vocabulary a lot as a Riemann sum. What's a Riemann sum? It's just your local estimate added up. And I'm not decorating the Riemann sum with indices I equals 1 to n, xi star, and so on, because I have no intention of actually manipulating this sum. This is schematic, right? This is schematic. You take your local estimate, add them together, it should estimate your quantity. What's the author doing on the right? They're showing another local estimate with more rectangles. Okay, delta x is smaller in this picture over here. Delta x is smaller, means you have to use more rectangles, but it means they fit better. So it's a better approximation. Take the limits of this thing as delta x goes to 0, and we should get the exact volume. So let me just scroll down and I can reveal. Yeah, the author is referring to this figure. It's called figure 3 in your book, so I've labeled it with the same number, although it's kind of the first figure I'm referring to. So the volume that you get by revolving this region in figure 3 about the y-axis, this formula is specific to that. We'll talk about how to modify that in the second part of section 6.3. But you're revolving that region around the y-axis. It generates a solid. We're just taking the limit of these Riemann sums. So notice that our local estimate just becomes our integrand. There's your 2 pi x f of x, and in the limit, delta x becomes the infinitesimal differential dx. What are a and b? A and b are the extreme x values, and for this to work, a had to be positive and b needs to be bigger than it. All right, so then, in other words, the y-axis cannot pass through the interior of the region, otherwise some of these shells will sort of spin on themselves and we double count. So this is the kind of main result. It's our first learning objective of the lecture. What is the volume for computing, or excuse me, what is the formula for computing the volume using the method of cylindrical shells? It's this thing right there. So that's called the cylindrical shell formula. All right, so any directions where somebody says, compute this volume using cylindrical shells, you're using that formula. Just like with disks and washers, it has a constant built into it, 2 pi. I usually like to write that out in front, right? It's a constant. And then what's the pieces of this thing? Well, x, the distance to the axis of rotation, f of x, the height of the shell, dx, the infinitesimal thickness of the shell. All right? Length times height times thickness, volume is dimensionally correct. Okay, let's do a couple of examples. Oh, sorry, before we do, this is a nice picture too, kind of remembering that shell formula. Maybe I should have been looking at this picture when we were just having that conversation, but it's kind of a nice way to think about it. That this shell, it has a radius, right? It's the x coordinate. In general, we'll talk about this tomorrow, it's the distance to the axis of rotation. So that 2 pi has to get multiplied by that distance. You think of that as a circumference in the shell. When you unwind the shell into the slab, it's the length of the slab. All right, the height is the height. It's the function value at x. Dx infinitesimal thickness. Length times height times thickness is volume. It's a nice way to remember this formula. Now we'll go back to our example. You can stop the video and go back to look if you want, but this was the example where we were taking, I can write it here, f of x was the function 2x squared minus x cubed, and we were looking over the interval from 0 to 2, revolving that thing about the y-axis. So using the cylindrical shell formula, stop the video and refer to this if you need, but look, I've got my circumference, there's my 2 pi x, I got my height, comes from f of x, it's this cubic polynomial, I got my thickness. All right, so like I said earlier, the 2 pi, and I'll almost do this just from the very beginning, it's a constant, it goes out in front. I distributed x through here to set this thing up for integration. So that bumps the exponents up by 1. Then the antiderivatives, they're power rules. So elementary antiderivatives, add 1 to the exponent, divide by the new exponent. And I need to evaluate that from 0 to 2. I'm skipping the details. You can correct me or verify with me in an office hour or however you like that integral computes out to 16 pi over 5. 16 pi over 5, and again, I'm not putting any units in these things that are contextless, but this would be units cubed, whatever the units are. It's a volume. Nice. Let's do one more example, and then I'll leave it there for this video. We can do some more examples in the online class or in an office hour if you like. So here I've got a region. It looks kind of like the previous region, but it's different. The function here is f of x equals sine of x squared. Okay, and I'm plotting it over the interval from 0 to the square root of pi. I don't know, it's pretty small on the screen there, but that says square root of pi down there. So we're looking at the region R bounded by sine of x squared, the x-axis between x equals 0 and x equals root pi. Okay, so it's as shown there, and I'd like to find the volume of it. It's the directions. Find the volume of it as of the solid that results from revolving that region R around the y-axis. You can kind of imagine what that solid would look like. like a jello mold or something like that. Okay, so we're going to revolve r about the y-axis, find the volume. We're going to use shells. We're going to use shells. I'm talking a mile a minute, but it's probably worth saying here that washers would be difficult for the same reason. As an example one, I don't know how to solve this function for x. Well, I mean, if we do, we're going to involve inverse trig functions, and then it's not going to be so clear for a segment given by a y value. How will we find those outer and inner radii? It looks like it's going to be sort of subtle at best. Shells means we don't need to worry about that, right? If we're revolving around the y-axis and we're giving something as a function of x, it's sort of out of the box ready to use shells. So what do we have to do? We just have to set up the integral correctly. This one I'm going to work with you. Let me try to leave the region in partial view here. So using our shell formula, the volume of this thing, I like to put the 2 pi out front. I'm going to do it. So 2 pi times the limits of integration would be, 0 to square root of pi. And then what do we have to put in? The 2 pi, remember I put it out front. So it's x, distance to the axis of rotation, f of x, that's our sine x squared, dx, infinitesimal thickness. So there it's set up. Now I don't need the picture anymore because now it's calculation time. So how to do an integral like this? Well, it's the integral of x times sine of x squared. So I think that's going to require a u substitution to find the antiderivative. I haven't said this very much, but for those of you, I mean, I didn't do very much review here, but I can post a link on the Canvas page from my Math 109 class this summer. All of my lectures from Chapter 5 on integration, and in particular u substitutions, are all on YouTube. So if u substitution is something that you are feeling a little rusty about, you can go back and review those examples there and then ask me some questions about them. Here, I'm just going to assume that it's going to go okay with u. So I'm going to let u equal x squared. So du is equal to 2x dx. And since I only have an x dx, I'm going to solve that for x dx. X dx is, pardon me, x dx is 1/2 du. So now I'm going to start replacing. The 1/2 is a constant. I'm going to pull it out in front. So this is the sine of u du, but I need to change my limits of integration. Right, I need to write u values here. 0 and root pi are not u values. But this equation converts x's to u's. So let's just use it. So if x is equal to 0, well then u is 0 squared. That's also 0. I'm going to make a little room here. If x is root pi, well then u is root pi squared. That's just pi. Okay. So there's our new limits of integration. 2 times 1/2 is 1. Antiderivative of sine. I got to be careful here. I want an antiderivative of sine. That's the opposite of cosine. And we need to evaluate that from 0 to pi. So we end up getting pi. I'm going to put the minus sign out front, so it makes the arithmetic a little bit easier. I'm talking about this minus sign, putting it out there. So now in the parentheses there, I need to take the cosine of pi and subtract the cosine of 0. And hopefully your trigonometry is sharp enough that you don't need a calculator for those, although it's okay if you do, but the cosine of pi is -1. It's nice to know these values because then you don't have to stop and kind of interrupt yourself. The cosine of 0 is 1. So what do we end up getting? Negative pi times -1 minus 1. So that's all 2 pi. And again, that would be units cubed. Okay, well, we just did 2 examples. I hope that you're going to do all those things in the practice problems in your text. It's the absolute best way for you to master this stuff and become competent before your exams. There's also a quiz on it. And thanks for listening.